Okay. Yeah, welcome to the study group session for the third lesson. This time it's a little bit, the time frame was a little bit short. So the session is only like, I don't know, 2 days ago or 2.5. I couldn't even watch the complete session this time, so I had a lot to do. How is it for you? Did anyone also not watch the whole session because the time frame was too short? Or did you all participate live?
I was live.
Oh, okay.
I listened to it afterwards.
Okay. So, but you could all make it through the whole session?
Yes, but I'd recommend skipping the first half hour because they go back and forth and you start over again.
Yeah. Okay, so let's see what we will do today. Okay, so I left the intro from the last times, but I think most of you will not participate the first time. So I will not talk a lot about the study group itself, and then we can go into the recap of lesson 3. As I said, I was not able to watch the whole lesson, but I have some things I want to talk about from lesson 3. And again, feel free to jump in, unmute yourself, and talk about things you want to talk about from this session. Just half an hour ago, I got 2 more people that want to show something. So we had just one presenter. I don't know the real name of Ed Hawaziti. Is he here in the session?
Yes,
no?
I'm here. Yes,
cool.
I'm here. Yeah.
Awesome. So your name is Haida, right?
Yes, Haida, yes.
Haida, okay, awesome. So he will show something about how to visualize model architectures. That's pretty interesting, I think. Kojak's, we will go on with his discussion. He started earlier on Slack about analyzing spectrogram images. I found that very interesting because it's kind of transferring the time-based audio domain to the image recognition domain. Pretty interesting stuff. And if you have time, Sanyam is going to show something about the Doodle challenge. He just said that he can show something for that. And also maybe if Christian's on the line, he can just very quickly show how he managed to deploy his guitar classifier because he was mentioned by Jeremy in the course, and that's pretty cool. So congrats, Christian, first.
Sure.
By the way, is he on the line, Christian? Are you there?
I'm here, yeah. Sorry I was late.
Nice. Oh, no problem.
Yes,
okay.
Also from the chat, just quickly. So there are some people didn't watch the lesson, some people did watch it. Jess found it more advanced, complex, and also would like to hear the discussion about deployment. So if you have time, Christian can show us his famous guitar classifier.
So I think the stuff you packed into one lesson pretty much tripled this time, and we just had 2 days for this. So let's see what we will talk about. Okay, yeah. Again, the study, we are doing rotating hosts for the study group. Today I am hosting it, and we will rotate it. I think you will know most of these guys from Slack. Again, on how the study group is, how we do this. We have the Fast.ai Slack channel. I think is there anyone not on the Slack channel? Just post on the in the chat. I think pretty much all of you will be in the Slack channel, and we are doing this weekly sessions like today. So if you are first, just write in the chat, and then Mikhail is going to point you to the right direction. Yeah, just like the last times, we want to do this mini presentations. Fortunately, we got 3 now at the last minute for this session, And you can just reach out to me or any other of the hosters on Slack if you would like to show something, or even if you would like to talk about something from the course, just reach out and then we can bring it up in the schedule for the sessions. Yeah, again, I mean, this time it's very hard, but we are trying to keep pace with the live course. That makes sense. And this time, in opposite to last time, we're going to focus on homeworks and projects. Yeah. So the schedule tells me that next time, the next live session is on Tuesday. So next time we'll have some more time until Saturday. And so this is actually the shortest time frame this time. Yeah. Okay. So now, I don't think that we need to do the recap of the last session. The video is going to be, I don't know if it's on YouTube now. Someone asked me a few days ago, but it will be online in the next days when it's not online now. Okay, so let's start talking about session 3 or lesson 3. Okay, so one cool thing, maybe I can do that at the first point. Someone from the live session in San Francisco created this searchable video player, which I found pretty cool. I think the videos that are shown here are the edited ones. So lesson 3 is not online yet, but what is pretty cool is that you can kind of search the transcript from the lesson. So when Jeremy says something, let's say, what was lesson 2? I think gradient descent, maybe. We find that. Yeah, and then we can click that. Oh, awesome! It's jumping to the right place then. That's pretty cool. So if you want to search specific things in the videos, Jeremy mentioned that it's the Google speech to text system, and that it's not always that good, and that they are maybe doing a speech to text model that's specifically geared towards the Fast.ai videos. That would be pretty cool. So
Kai,
yeah.
What if gradient descent phrase is mentioned 5 times during the video? You think, does it find the first one, and can you skip from one to the next to the next?
So let's see what's happening here.
I think it will get all the 5
yeah
different.
Yeah, I think this is the first one, and then second, and
okay.
Yeah.
Mm-hmm.
Okay. Okay, so this one is pretty cool. Let's go back. Okay. And then the next thing that I found really interesting was this data block API he was talking about. So how the data set and data loader things from PyTorch and the classes from PyTorch are used to create the data bunch in Fast.ai. That was pretty interesting. I didn't know how that it worked like this. So what do you think about this API?
Yeah, I mean, I think that the main thing around this was that it just gives you the flexibility that you wouldn't have got using the, what he taught us in lesson 1. So this basically means you've got loads of options now.
Yeah. There are these pretty cool notes here, and they are.
So what I was trying to do. Can you hear me?
Yes.
Can you hear me, guys?
It's a little bit scrambled, but I can hear you.
Oh, sorry. Okay, sorry. I have a question. Maybe you know how to do it. So what I did train the model. I have weights that I saved and I have data, I have classes that I've saved. Now I've deleted the training set, so I don't have it anymore. But I have the test set, and I want to now do inference on the test set. I couldn't a bunch for which you also need the training set and all the labels to do it. So it seems like I was not able to do inference on the test set without having data bunch created. And for that, I need the training set. And that was huge data set, which I don't want to download again. That was like 500 gigabytes. It took several hours to do it. I was hoping I would be able to do inference just having the weights for the model, the trained model, and classes even I have, but it didn't work. So I was just thinking maybe you find a way, or you know how to do it, or is it possible to do it?
So to understand what you mean, so you have the test set and you have the weights. You can load it into the model, but you can't do inference on the test set because it don't accept it without the training set.
Yeah. So the way I understand, I need to create. I need to do learn.pa, and for that it needs the data. And I cannot create data without, at least that's my understanding, I cannot create data without training data and labels for the training data. So I'm a little bit stuck. I would hope that you can, it's like when you predict the, like all the web apps, you predict a single image, but so I would like to do the same, but I just want to predict on the whole bunch of images.
Well, I think you could probably just pass in like an empty training set. I don't know if you've tried that.
Yeah, so I've tried to like put none to instead of putting the folder, the train folder, I put none, but it kind of complained about it. I tried to put like a random folder there, but then it complained that the training labels and training images doesn't match. So I kind of like try a couple of things, but I would hope there will be like a way to do it without fooling the image data bunch. So far, I didn't find it. Maybe there's a way. Maybe I just don't know how to do it.
Yeah, I mean, the other option is like you could just kind of do it outside of Fast.ai. So just load your model, just kind of pass the batches to it. Because if you're just trying to do inference, then you don't really like need all the other stuff in the library. I mean, you might not want to have to do that all yourself, but that's another option.
Okay, yeah, I have a look into that. Thank you. Yeah.
So the model is just like a PyTorch model, and you can just use that. But isn't it possible to just load weights into a model and do inference without?
Well, that's what I was about to ask. I mean, how is that different of doing like a regular inference, like I did in the web app? Because you need you need to load a different method instead of the single from classes. You need something else, or
yeah. So I've tried a single from class. So I've put the classes and the empty data folder, and I did try to run the learn.tta, and it doesn't require isTest true anymore. They just changed it, I think. But it showed me an error, and the error was, I forgot what it was now, but it was an error. Yeah, so I tried a couple different things, but so far I'm just like still trying. Yeah,
changing APIs is a bitch as well. Yeah, that they change actual core functions around.
Yeah.
Okay.
So just a question for you, Mikhail. Maybe I've misunderstood you, but if we are, for example, if we're using ResNet 34 or whatever, right? Don't you just say it's a ResNet 34 model and then you load the weights and you get your prediction that way?
Yeah, I was hoping I can do that, but so far I wasn't able to find a function or method in Fast.ai to do it. Maybe it's there. I just don't know maybe where to find it, but yeah.
I posted my 3 lines of code in the chat, so I don't know if I don't really follow if that's different what you need.
You have the single from dataset, and then you have transforms. Single from classes. You have single from classes,
And
So
then basically a model state, a load state dict, and then load the torch.
Okay. Yeah, I've used slightly different code that I found on the documentation site of Fast.ai.
I found this one too.
Oh, okay. Oh, maybe they've changed it then. Yeah, so
it was from someone else's. So it wasn't from the docs.
Okay, I'll try that one. Maybe that will work. Thank you.
Okay. Yeah, but so this data block API and the ability to kind of quickly change things here that's a really cool thing. At least I found that in this lesson. And then again, and we had this in the last course too, which is progressive resizing, which is kind of I mean, it's not that complex idea, and it seems to work really good. So did anyone try that in your projects?
I have a question about it, but I think we kind of figured that it should work. So I was wondering, I mean, with the ResNets, we always used like 224, 299. And I think in the lesson, or at least in the chat, people were talking about 64, 128, 256, 512. Is that like suboptimal, or the model doesn't care, or?
Well, I think so. When you kind of trained your net on, let's say, 224 by 224, and then you give it a picture that it's like 2000 by 2000, then the filters will not match the features. So a tire, for example, when you want to classify a car, is much bigger in this, much more pixels, stretch out on much more pixels, and then probably the filter is not, cannot find a car because it's too big.
Yeah, I think I get the concept about the progressive stuff. I was just wondering if I need a multiple of 229 or 299 instead of having different steps. If the steps matter in any way, like I kind of figure, okay, you should have a multiple, but I wasn't sure if the ResNet is trained on 229, if the multiple then should be like double 29.
Christian, why multiple of 229? So let's or multiple of anything. Why do you think it should be a multiple or something?
I thought that's the idea, that these progressive resizing is always like the next kind of increment of the resolution. I don't know. It's just guesswork here.
Well, I think it's kind of, you have smaller images, and then you can train the net very fast, and then you have good initialization weights, and then you go on and make it bigger and kind of get more of the details, and then when you make it bigger, it's getting better.
Yeah, probably.
Yeah,
and also up the trial.
Also on the computation limit side also, if we train bigger images on a single GPU, sometimes it gives memory errors.
But could one, for instance, maybe I'm just dense here, but could one, for instance, go 229, 300, 350, 400, or is that like?
Yeah, you should be able to do that. The only limit, I think, is going to be how many times it like cuts your thing in half with like max pooling or stride equals 2. But
yeah, okay.
But I think in terms of like actual multiples, I don't think it has to be a multiple of 224 or any of those numbers.
Okay, cool.
But I think the computation you need is it's not factor 2, it's quadratic, right? So when you have bigger pictures, you need a lot more computational power.
Because I've faced errors with like if I have a bigger batch size and a bigger image size of ResNet 50, it fails on a single GCPU with out of memory error.
Yeah, makes sense. Yeah.
Okay, just one question on this. You know, I think typically in ResNet they also have like all of the images tend to be a certain size. Was there any? So how does this play in with that? So the fact that we're actually changing the sizes now because it seems to provide a better model. Because My experience in the past was you'd always use this certain size for ResNet, but now it looks like we're changing it because it seems to provide a better model. Does anyone have any thoughts on that?
Yeah, so I think the idea behind the progressive resizing is that you, isn't it just the idea that you want to train your model faster? You want to get to a good model faster, and then you start with 64 by 64 images, and I mean, it's a lot smaller, so there are not that much.
I think you're right. Yeah, I think you're right. Okay, fine, thank you.
Yeah.
So it's not actually about the model can abstract like features on different sizes within the image. I thought that you get like the capability that it can detect larger objects or smaller objects as well. Is that a misconception?
I think it will, but the idea was to experiment faster to get to a decent level.
Okay.
And the bigger images will give all the details, but you might not always have that much time and computation power. So with progressive resizing, you can get to it faster and maybe better as well.
Okay, makes sense, yeah.
Generalization wise.
Yeah, I wanted to try it out. I wanted to train a second batch of models for the app. Yeah.
Yeah. So I think they used this progressive resizing in this what is DOM bench competition they won for very efficiently training on ImageNet, and I think that the reason behind that is that you can start very fast. You get pretty good results pretty fast, and then can do transfer learning and go on that.
And I think someone broke that record a couple of days back too.
The DOM bench record?
Yes, Jeremy is on Jeremy's record. Someone broke that.
Yeah, Jeremy tweeted about this, and they've smashed it like 2.5 times. That was like...
Oh.
Isn't that the NVIDIA block we were discussing previously, where they basically said, okay, how they actually shaved off seconds and here and there, and
well, there's a nice post about how they did it. I didn't read it, I just scanned it. They did a couple of interesting things.
Yeah, pretty in-depth thing.
But it was not using Fast.ai?
I think, I'm not sure. I didn't read that in detail.
Yeah, me.
Okay. Yeah, interesting.
Yeah.
Can I ask a very simple question? This is incredibly basic, but
absolutely.
Yeah, so I've had a bit of a brain freeze. I've seen a whole lot of this, this freeze, well, brain freeze. So anyway, I've seen a whole lot of these, cycle of freeze, unfreeze, and then fit one cycle. And I'm a little bit confused because I thought whenever you do a fit one cycle, you're adding like a fully connected head with the relevant number of classes. So in lesson 3, he did several of these. And I know it's doing some sort of training, but if someone could define or just explain what we're doing when we do these multiple freeze, unfreezes, and fit one cycle, I'd be really grateful.
Can you all mute yourself and just unmute yourself when you are talking? We have some bad feedback noise here. Okay, so I think that this applying a new head to the network is really you do it all one time at the beginning of your training. So you take the vanilla ResNet with 1,000 classes, I think, and then you cut off the head and apply a new classifier head on that, and then everything you do after that is all the retraining stuff is done with the same network. Then it's not changed anymore. Then so when you unfreeze and then retrain, you always use this head you trained in the very first step of for your data set.
So it's only when you do the fit one cycle the first time that you're actually adding that new classifier.
Yes, I'm pretty sure, because I mean it's the classifier for your data set.
Yeah. Okay.
Yeah.
So how is it that when you do a couple more of those fit one cycles, you're not changing the head anymore? Because there was like this, it's like he looped through this freeze, unfreeze, and fit one cycle, and that got me a little bit confused.
Yeah, well, in the very first step, you take this features that are generated in the ResNet part, so in the convolutional part of the network. Then you get this features in your feature maps, and you use those features to train the classifier for your specific data set. So let's say you just have like 20 classes instead of 1,000 classes. Then in the first step, you train this classifier to use the feature with a frozen ResNet network. And then you get a pretty decent classifier in the head. And then in the next steps, you unfreeze the whole system. So there are then a lot of weights you can retrain, and you gradually feed your data through the network to kind of fine tune the network.
Okay, so so just one clarification on that. So okay, so why is it that doing that future what's it called? So I get the fact that the first time you do the fit one cycle, right? You're basing it based on the relevant number of classes for your use case with that model. Why is it that when you do a fit one cycle later down in the code, it's not doing exactly the same thing, which is fitting your class, fitting another thing to the end of your class? Because I get why you'd need to do it the first time. I don't understand why when you do a fit one cycle the next time around, it's not doing exactly the same thing.
Because in the next time you unfreeze the ResNet part of the network. So the ResNet learned the features that are necessary to classify the ImageNet pictures. But you can, when you unfreeze it, you can bring it to learn the features that are important for your data set. So it's actually the ResNet part of the network is changing when you unfreeze and then train again.
And maybe you're confusing that. I think it's actually producing this network in create CNN, and basically there already it chops off the head, right?
So say that again, Christian.
I'm pretty sure that it's actually chopping off the old head of the network in create CNN, because you can specify a custom head there. So basically, that's the very initial stage of defining your model, and then later on, it's just like freezing and unfreezing different parts of the model, but you don't change the structure anymore. Yeah,
and freezing and unfreezing really just means that you say, okay, those weights can change or those weights can't change. Exactly. And when you say they can change, then you can basically you retrain the whole ResNet part too. Because it probably learns some features from ImageNet that are important also for your data set. But when you allow the network to learn, to relearn and learn about new features that are specifically important for your data set, then you will get better results.
Okay, great. Well, thanks a lot. I'll take a look at the chat messages also, and if I have a question, I'll put on the Slack. Thanks.
Yeah, sure. Okay. So the next interesting thing was the unit architecture, and so I think I watched the whole part on the segmentation part, but I did not go on in this lesson. And so did any one of you do something with segmentation?
Basically just ran the notebook, didn't really dive in.
But I think it's a really interesting architecture, and it's like with so many other things in deep learning, it's kind of incredible that it works so good.
Did anyone read the actual paper? Probably not, huh? Not enough time.
No.
That's from Freiburg, right?
I just looked at it. This seems to be nice also video explaining how this unit works. Quite short video from the authors.
Yeah, I haven't really heard about it before, so it should definitely be worth checking it out.
I came across this when there was Kaggle Salt something competition, and pretty much everyone used that one for that competition.
Yeah, I did the Salt competition, and yeah, pretty much everyone was using UNets. But I guess the interesting there was people use like different bases. So like some people use ResNets like in Fast.ai, but some people use like dense nets. Pretty much any CNN you can kind of plug into the architecture. So that's kind of an interesting part, because I think the original UNet was actually just VGG. So it's kind of evolved over time.
Yeah. Also, when I prepared for the first EMEA meetup, so not the study group sessions, but the meetup where I showed or presented something on capsule networks, and I had a look into SecCaps, which is a segmentation architecture based on capsule networks, and that's at least what people say. It's pretty promising because segmentation should, in theory, work a lot better with CapsNet architectures than with convolutional architectures. So maybe in the future, something CapsNet can be a predecessor for UNet. Yeah, what I also found very interesting was the training with reduced accuracy, and particularly one phrase or one sentence Jeremy said was that quite often in deep learning you will generalize better when you get inaccurate. That was pretty interesting, I think. Did anyone of you try this this sort of training? I think you need a very new NVIDIA graphics card for that.
I think that's the problem. Yeah, you basically need one of the two 28s.
Yeah.
I don't know which of the old ones have it.
Yeah, so I have a 1080 Ti, and I think it's not possible to use this.
Mm.
Okay, so it's probably
potentially for building your own box. That might be really cool. I don't know. I didn't really go into it, but if it like a 2070 should be quite cheap when they are available in the market, and then you could basically get away with less memory because you can basically halve your memory requirements.
Yeah. So do you know the specs of a 2070?
It's 8 gigs. 8 gigs of memory.
Yeah. 8, okay.
So like if you do FP16, can you do it on any type of network, or because you basically don't using the whole 32? So would that work with any?
I think it's good, would work with any CUDA code, I think, because
but I think some parts of the process still need to be in 32. I kind of remember that either the backpropagation or something needs to retain the high resolution.
Okay, yeah, that's possible. I didn't look into that.
Yeah, I would think so.
Go on.
Yeah, because otherwise why we would use the 32 for the older version? Because I would say that it's needed for something, but maybe not actually. Maybe not for deep learning. I'm not sure.
So what I know that this FP32 stuff in the graphics card, I mean, you don't need that for graphics processing. There the lower precision is enough, but they did that because I think they did that because those graphics cards and the CUDA stuff is very often used in kind of numerical simulations, and this accuracy stuff is very important there because you kind of accumulate the error when you have lower precision. And I think since people know that for this deep learning stuff, FP16 is enough. I think they kind of changed their architecture in that direction.
So basically, this allows you to do a whole lot of these matrix calculations without storing as much of the actual calculations or your figures as the 32s.
Yeah, well, I don't know. So Chris, you mentioned that not for every part, but I think most parts of the networks and the numbers and the weights you save there and the calculations you do are with FP16.
Yeah, I can't remember. I think it was discussed in the forum somewhere. There's a 2080 thread, and I think it was mentioned that you can't go like 100% to the lower resolution, but you can still potentially save quite a bit. But it's still a bit shaky, so it's not really super robust yet. And you need, I think, also the newest CUDA 10, I think.
Great, thank you.
Yeah. Okay, so then let's go into our mini presentations.
I had a question.
Yeah, go ahead.
One question about Jeremy suggested maybe trying out a regression example during the week before the next lecture. So part of the challenge there is having a data set, a labeled data set. In fact, some podcast I listened to recently, the guy, maybe it was Talking Machines or something, he said when he goes to a conference, he goes around looking at a poster session to see what data sets people have created, because sometimes that can be more valuable than some methods that people have come up with for that particular conference. because lots of people can then look at the data set. But a particular question I have is, you know, do people have a good way of, if I have 25 images, how do I find the pixel location of some feature on the image that I point out, so that I can create a labeled ground truth data set? For example, I want to find all triangles and I download 100 pictures. Now I want to figure out the coordinates of those triangles. I mean, there are probably various tools and custom ways of coding that. But does anyone have an idea of how they might do that? Because that's sort of potentially the homework you would do, is a regression, like the location of the face example in the video. At some point, somebody had to probably hover their cursor over the face and capture the points of that pixel location and mark that down somewhere. And we have to do the same thing if we want to do that regression homework, right?
I mean, that should be the same problem like with the bounding box issue, right? Object detection. Basically, you need like, that's also done with the regressions. You need the model needs to come up with coordinates, and that's a similar problem. There's a couple of tools where you can annotate images, but I guess it's a lot of work. So I don't really know. I mean, box,
that is a lot more work. This is probably the minimum amount of work where all you do is
click somewhere.
2 numbers.
Yeah, I mean, I've seen a Qt-based Python library where basically which is used to annotate stuff. I don't know. I can look it up.
Maybe using PyAuto GUI also, we might be able to achieve something like this.
Mm-hmm.
But I reckon like there's so little time till the next session that few people will actually create their own regression data set, because I imagine that's quite a lot of work.
Well, maybe if we, you know, we start out with this pre-trained object detection model, ResNet 34, perhaps we only need maybe 10 or 20 to get something working.
Okay.
Yeah, it would be interesting to know how many you would need, and if it works with such a low number of images.
I have a question. You know, in the lecture, he mentioned people doing projects with video capture, and they're just using some sort of software to pick out video frames. Does anybody know what kind of software that is?
WebRTC, I would imagine.
WebRTC?
I think that's for grabbing frames when you have a video camera streaming. It'll grab them.
Okay, thank you.
If you're talking like live, like not processing video files, but actually like camera input.
Oh, how about just video files that's pre-recorded?
I think there are
an OpenCV for that.
Yeah.
Yeah.
Okay, thank you.
And also keep in mind that and Jeremy also said that in the lecture, that you have to carefully design your training and validation set, and that you don't just mix them randomly up, those the images, because then it can be very easy for the model to find pictures that are almost similar one frame to the next in the training and the validation set. So always use dividing by time. So use images from the first part of the video, and then from the second part, from the last 20% of the video for validation.
Okay, yeah, good point. Thank you.
Okay, so Haida, you want to take over the screen and show the visualization?
You can hear me, right?
Yeah.
All right. So sharing.
Let's stop sharing.
Do you my screen?
Yeah.
All right. So I was working with Cedric. We tried to port Fast.ai models into Android. but it wasn't an easy task. So during the debugging, what the problem was, I tried to search for a visualizer for the model. Since the model, our model that we generated differs with a few bytes, few hundred bytes than the Facebook repo for the example of the Android PyTorch to Android porting. So I found this one. It's called Netron. It can support the Onyx format and Keras, CoreML, Cafe, but for the PyTorch, it didn't work. Since it's an experimental support for Cafe and PyTorch. So we try to make so I have this this in the forum. I posted. The workaround was by doing this 4 or 5 lines of code. So you have to install in your system the Onyx. Onyx. This is a library for porting a standardized format of the models, and it's supported by all major libraries like TensorFlow, MNXT, PyTorch, Keras, and you can install it. But unfortunately, I didn't get to install it easily. I had to compile the Onyx as seen in the example. Yeah, just a minute.
And did you install it on your Windows machine?
No, Ubuntu 18.
Okay. Yeah.
So this is the way to install the Onyx library, but this didn't work. So I had to compile it as shown here in the steps here. You can also build and install Onyx locally from the source code. So this worked fine without problem. So after that, it can make a dummy input and an output name as an input names. And this one line code will export your model. This is your model. This is your Fast.ai model, learn.model. And this is the dummy input. Dummy input is just for representation, so that in your graph you see this name. That this is the actual input one. And then you assign the path of the model. This will be the file name, and that's it. You will find the file and put it in this this application, which is available on Mac, Linux, Windows, so everywhere. So what I got from, for example, for ResNet 38 is this graph. This is the input, and going down all the way down like here.
Oh, that looks pretty nice.
Yeah, it's a pretty large model. So, yeah. And until going to the output, from input to output. So nice. This is the best way that I found for visualizing our models. If you have something else, please share.
No, that looks really good.
It looks super cool.
Yeah.
Just installing now.
This is the link. I will share it with you.
So you can maybe and all the others that are posting stuff on the chat here, please also post that on Slack, because the chat is gone when the session ends. So just post it on Slack, then it's preserved.
Sure.
Yeah, very nice, very nice.
Really good.
Okay, so now we can talk with Kojax maybe. He posted something on, so he's trying to classify images from sounds or spectrograms. Kojax, are you on the line? Kojax, is that correctly spoken? So he's at least in the chat, I see that. Okay, so let me go through what he wrote in the chat. He is trying to classify spectrograms. So if you don't know what a spectrogram is, you definitely have seen a spectrogram. It's kind of a transformation from audio data that kind of have this waveform that you know into a time-independent domain, and you kind of plot the amplitude of each of the frequencies you have in your data. And
maybe you can open the link in that chat. There is a picture of that.
This one here. Oh yeah. Wait. Let me share the screen again. Yeah. Can you see my screen?
Yes. Yes.
Yes.
Okay. So that's what a spectrogram looks like here. And so this is this whole picture is for one specific time frame, right? I mean, correct me if I'm wrong. I'm not an audio expert here, but so in this axis you have frequencies. I think the color is the amplitude, right? And the this direction is the time. No, is it like that?
Time is on the x-axis.
Yeah, right.
And frequencies are on the y, and the intensity, or the energy is in the color.
Yeah. So this picture shows one specific time frame of a certain sound, right? And so when you have different types of sounds you want to classify, then each one has a pretty unique footprint here in this amplitudes you see. And so you can use a image classifier to classify sound. And why can't I see the chat when I'm in presenting mode? Does anyone know how to get the chat here?
We can read the chat to you.
Okay, there it is. Okay, so his problem, I think, was that those pictures are not rectangular. And the question, if this is a problem, is it a problem that these pictures are not rectangular?
So I can speak to that. I actually tried running spectrogram analysis using the CNN last week on Fast.ai, and it actually worked great. I used the Google challenge that had been maybe 10, 11 months old on Kaggle, where there were a number of single syllable commands like stop and go, and then a bunch of other words that were not commands. And they basically wanted you to build a classifier that could figure out exactly what word was being said. So I used that data set, I turned everything into spectrograms. I used basically all the standard things we've learned so far with CNNs, although I did take out the transforms, and I got excellent classification accuracy. So I don't think the rectangular thing is an issue.
So you also did not use rectangular, but kind of this shape like this pictures?
Yeah, I ran it through, I created the spectrograms using Librosa, I think. Saves normal looking JPEGs that are, or PNG files that are not square, and there was no issue.
Okay.
What about the resolution there? I mean, I wonder, like with our kind of image sizes, it should be like really hard to pick up any wobbles there, or is it really enough? Apparently it is.
In the image that I see displayed on our shared screen right now, there really doesn't seem to be a lot of resolution, however, or a lot of differentiation, except at the bottom there. However, on all the JPEGs, or on all the spectrograms that I created, it was pretty clear that you could do activation on different frequencies across a wide range. And I think I used just the standard 224 image sizing, and that worked well.
Yeah, so you used Librosa, or whatever this library is called, right?
That's correct.
And they are MEL spectrograms over there, because I remember seeing some of them. They looked quite different than this blog post. They looked a lot more diverse, like a lot more action in the image.
Yeah, so I actually tried 3 different versions. There's a non-MEL spectrogram, which is just a normal spectrogram transform. Then there was the MEL spectrogram transform, and then there was a variant on the MEL spectrogram MFCC. And I didn't see. I actually found just with the both the MEL and the regular spectrogram both produced good results.
Oh, interesting.
So the shape of the picture spectrogram that you used is like this. It's rectangular without problems. It should be square, or it's not required to be square.
I don't think that it's necessary to be square.
Yeah,
maybe
I didn't even worry about that. Maybe I should have.
Maybe this is because of the train time augmentation, the TTA. If you remember, I don't know, because I took the version 2 of Jeremy's course. He said that his library is doing a training time augmentation. So he crops squares, but in different places. Maybe, for example, maybe 10 times, 15 times for each picture. And it would take random squares from everywhere. And then averaging the predictions or the training. There is a test time augmentation and training time augmentation. So
I think that what Andrew said, and I think Andrew said that he didn't use transformations and augmentation, and that kind of makes sense because you would distort the sounds you are trying to classify, right? So when you change the picture and squeeze it or turn it around, then it would be different sound.
Yeah, I wouldn't warp it or something. Yeah.
I mean, just train time augmentation. It can do without any augmentation. You zero all types of augmentation. Only the cropping is taking a random. So I
don't think that you would even use cropping here, right? I mean, you would lose part of the. So when you Andrew said that he's classifying words, right, Andrew? Words like go and stop and.
That's correct.
Yeah, and when you kind of crop the image, then you would lose part of the. So you would definitely destroy the meaning of the word, I think.
So just one question on that, Andrew. So if the longer the word, the wider your image, right? Or are all the images the same size?
Yeah, well, all the images are not exactly the same size, but they do seem to be. I think Google was trying to make this relatively friendly. They're all about 1 second long, roughly. And so I do actually think I saw somebody was posting earlier in the chat about a recent post that I also saw about why CNNs may not be good for audio analysis. And I do wonder if there are much longer snippets of audio, whether it starts making sense to think more about an RNN model where you have sort of overlapping windows of time in a sequence, because I think one large spectrogram for a big audio file might be a little hard to capture all of the nuance and specificity. So I think these really short audio files lend themselves well to something like a CNN.
Yeah, I've seen a talk previously where they used recurrent.
I did notice one. Oh, my audio might have frozen.
No, we can still hear you.
We can hear.
You can hear me. Okay.
Yeah.
I was actually to the point about augmentation. I was looking around on Archive to see if anybody had thought much about how to do data augmentation for audio. And I was initially excited at first. I found this one paper from China where it kind of makes sense, I guess. The authors decided to magnify spectrogram frequencies in a way that should mimic like things getting louder or softer as a way of doing data augmentation. And I thought that was pretty clever. But then they announced that they had like completely blown away the state of the art from like, I don't know, 50% recognition on some classification task to like 99.9. And I looked really closely at the paper. Again, this is just an archive. And it turns out that they had completely contaminated their test set with their training set. That's why they were getting such good accuracy. So I'm not actually sure whether their novel data augmentation system really works. I'd love to see somebody try that out with a little bit more rigor.
So Andrew, just a question on a really simple question on this, on how you interpret this. So, on what's being shared, the screen that's being shared, above the word frequency, for example, right? The orange bit at the top means like that's a little bit of, that's a higher frequency bit. How do you interpret that with all of the, the dark red, which is supposed to be the intensity of the sound?
I think it's a different way around. I think the color is the intensity.
Yeah. But so I thought the lines represent how high it is, right? Because that's the frequency, right? So how high that sound is.
This is the frequency. So when it's more bright here, then the frequency is higher. And when it's more bright here, the frequency is lower.
Okay.
And when you have, so the bright parts mean that the amplitude of this specific frequency is high for this point in time. And then the whole x-axis here is time. So this would, the image would go like this when you would record it.
It seems to me like this would have, I can believe that for 1 second burst, you can use a CNN on a spectrogram like this, maybe just 1/10 of the picture that we're looking at, one of those little small structures. I can see how CNN might be useful. But if you try to use with a full sentence or 10 seconds, I guess you would have the same problem that Jeff Hinton, why he created capsule networks, right? A CNN can identify a face not because of where the eyes are in relation to the nose. They could be anywhere, right? Your mouth could be above your eyes and your nose could be where one of your eyes is supposed to be. All those things, the network calls it a face, even though it wouldn't look like a face to us. Here, similarly, the time component, I guess, would just be lost completely, right? And a CNN wouldn't really be able to handle that if you had more than a short burst of sound.
Probably.
I think you at least need a moving window, basically. So,
yeah, I mean, but the time component is the x-axis, right? Or am I wrong?
Yeah, x.
Yeah, but this is just so you can only show one image at a time, and this is one fixed period of time. So it's not like a recurrent net, for example.
So in this case, if it's important which structure, if the large structure comes before the smaller structure on this plot, the CNN wouldn't be able to tell the difference, I think, right?
Well,
that's right. So my understanding is that.
Go ahead.
Can I show you test time augmentation for notes from the lesson 2 of last year? I can share the screen, just a few minutes.
Yeah, guys, I kind of have to leave on point today because I need to go now. But I will just leave the meeting and you can go on with the discussion. So when you want to share the screen?
Yes, sure. All right. So, do you see my screen?
Yeah.
So this is lesson 2 of the last year. It says that in test time augmentation, we have these pictures which are rectangular, as you see. So when we do the validation set, all of our inputs to our model must be square. The reason is kind of minor technical detail. But GPU doesn't go very quickly if you have different dimensions for different images. It needs to be consistent so that every part of GPU, so it should be square. So how Jeremy made the Fast.ai library is that to make it square, we just pick out the square in the middle, as you can see below. So this picture, for example, this picture, he takes only the middle square of it. So I don't understand how we can solve the problem with the with a spectrogram which is rectangular. If you take only the middle square. But for Andrew, the question is did you use Fast.ai for the Kaggle competition?
Sorry, I just got disconnected momentarily. I heard you ask me if I used Fast.ai for the experiment I was describing. Is that right?
Yes, yes. Did you use Fast.ai?
Yes, I used Fast.ai.
So you didn't worry about this issue, the square, picking up square from the rectangular images.
Yeah, my sense is probably what happened is that I had just used, I think if I remember correctly, when you pass in the image size to setting the parameters on the CNN, if you just pass one number, then it treats that as the number to create a square image. So if you just pass in 224 instead of 224 comma and some other number, it just makes your image into 224 by 224. So I imagine it just slightly warped the shape of my image to smush it into that square. That's probably how it got a square image.
And how was your error, the validation error?
It was very good, actually. I think that if I didn't submit to Kaggle per se, I think the best on Kaggle was about 91% accuracy. It was just a raw accuracy metric. And mine actually got 93, but I suspect that the reason for that is that I didn't batch, similar to what Jeremy was talking about this week, I didn't batch the train and validation sets where each speaker was kept only either in train or validation. And I suspect that there might be something about the fact that even if you say stop in the train set, if your voice is still saying go in the valid set, that might be some data leakage that inflated my classification. But even so, like it still seemed to work pretty well.
I see.
Would you be able to share this stuff, Andrew? Would you be able to share if you've got it on any GitHub? It'd be interesting to take a look.
Yeah, sure. I've got to clean up my code and I'd be happy to send it over. Actually, one thing I thought I might share, I know we're over time, but for any of you still curious about the translation from sound to spectrogram and exactly what that means, I do have a couple of images on my notebook that might clear that up. I don't know if anybody would be curious to see that. Just
yes, please.
Okay. May I take the screen share?
Sure.
Okay, let's see here. Can you see my screen?
Yeah.
Okay, so this is the word bed, and the very first image is something you've probably seen on any kind of audio analyzer before, just the normal sort of frequency activation. The one just below it, that's the non-MEL spectrogram of somebody saying the word bed. And you can see there's the darker colors on the spectrum are silent, silence or low activation, and then the brighter green is activation. And so if somebody's quiet, then probably they put their lips together right around 0.17, then the main action is in the middle, and then it's quiet again. So a MEL spectrogram, this is exactly the same thing. It looks like this. Actually, I took the log of it because I read somewhere that that's what you're supposed to do. It's not that different. I mean, the colors are different, but the basic idea is the same. The MFCC, which has a word in it that I don't actually know how to pronounce out loud, but you can look it up if you're curious. This is it's just a transformation of the MEL spectrogram, and I understand that under some circumstances it works better, although I'm still trying to learn exactly when. But I thought maybe the most interesting thing for me that really kind of brought to life exactly what does this spectrogram mean is, it's a little weird because we have these 3 dimensions encoded. It's time on the x-axis, but each y-axis band is just one band of frequency. And so I actually found it helpful to plot it in 3 dimensions here. So you can, it's exactly the same as what we saw above, but instead of just there being a color activation, now there's a redundant activation on a z-axis as well. And so this is really what it's trying to describe in terms of when and where across the frequency bands that you're seeing sound get activated. That's all I wanted to show.
Nice.
Are all spectrograms mainly in the middle? I mean, the changes you see, as you show us the spectrogram here, the word has been spelled out in the middle. So maybe all of them like this?
So I think that that's really just a function of, there's 2 types of middles you can have. I'll go back up to here because it's almost easier to show. One middle is in the middle, if you will, of the y-axis, which would be like the middle of the frequency spectrum. And for that, I would say definitely not. Depends on the way that your mouth is perturbing the air will determine what frequencies are most active. On the x-axis, that's also not necessarily always going to be in the middle. It just so happens that on these recordings, there's a little bit of silence in the beginning and there's silence at the end. And then the word in the middle is really where the action happens. So you could imagine if there was a lot of noise in the beginning, silence in the middle, and then noise in the end, then you would see almost the opposite pattern here.
Yeah, yes, actually for the frequencies, it's okay that it's not in the middle because for our crop that I showed you in the Fast.ai, it will take it all because this is the least dimension, the length. But for the width, as you see, if we take only 1/3 of the time, we take only the third square in the middle, then it will represent all the words spoken because it is spoken in the middle only. So are all the data set has been captured like that?
No, not exactly. So I see what you're saying. And in fact, that is one sort of good hygiene practice that I encountered that I didn't actually do on this audio, which is you can essentially perform the equivalent of trim or strip on strings to audio files so that it just kind of throws out all those stuff where nothing's really happening. So a lot of people do kind of try and zoom in on where the action is. However, you could imagine that a 2-syllable word like 0, for example, has a little bit of a pause as I transition from Z to rho, compared to a word like bed, which is just this plosive sound, and then it kind of dies off quickly. And so then you would see you'd see almost kind of like a bimodal activation in the middle for 0, whereas bed would just be more like this single chunk. Does that make sense?
Yes, thank you.
Sure thing. Okay, guys, that's just what I wanted to share with you, but I'm going to hop off now. Thanks for your company. See you next week.
See you. Bye-bye.
Okay, so do we still have a host around?
I don't think so.
I guess that makes you the host, Christian.
That's what I feared.
Hey, I'm just on the jump out of the door, so you want to go on? So I can leave it on, but we can also.
I don't know. I mean, I don't have to show this guitar stuff. I mean,
yeah, we can do that next time.
Exactly.
Right. So next time, Christian, and also I think Sanyam has something to show. So we have already 2 mini presentations for next time.
Yeah. Cool.
Awesome.
Cool. Thank you, guys.
All right.
Okay. Bye.
Bye.
See you next week.
See you next week. Bye-bye.
Bye.
Bye-bye.